Okay, chapter 9 worksheet. It says chapter 10 worksheet on it. Just my mess up. Hopefully I'll fix that the next time somebody watches this video. Okay, so all we're looking at these three residual plots. Is a linear model appropriate? So this one I would say is appropriate, and the reason would be you have random residuals. This one is not appropriate because we see curved residuals. Not appropriate here because we have the change in variance of the residual plot. Okay. So, pretty straightforward. Everybody good? All right. So number 2. Write the regression equation. Just going to jump in right away. Remember when you see these, you see the coefficients. The first one is B0. The second one is B1. So y hat equals B0 plus B1 x. So 0.154030 plus 0.065052. X is always here, so this is the tar, probably in milligrams. I'll just put tar there, and then we have to figure out y. There's a couple places we can figure out y. It's got tar down here as x, and it's got nicotine, both in milligrams. So nicotine is what we're trying to predict. Okay, now one of those things that you have to have on any test, how do I do the slope? The slope is the 0.065. Remember, you always put y over x, so it's the 0.065, that's a 0, over 1. So y goes up 0.065, that means nicotine. We predict 0.065 more milligrams of nicotine for every 1 more milligram in tar. Okay, hopefully something you've got down at this point. It says interpret the slope for the next one. I think I made a typo. I think what I want is the y-intercept. I'm not going to do the same thing. So we're going to change that one to y-intercept. Hopefully I get that one fixed for the future. But if we were to put 0 in, if tar is 0 milligrams, we predict. Now, if you were to put 0 into there, it's going to make that disappear, but we predict 0.154 milligrams of nicotine. Explain R squared. We look for R squared. It's got 92.4, so I'm just jumping in, going through these. Again, pause the video if I'm working too fast, if somebody's watching at home, or here if you need me to try, but I'm just planning on going through 92.4% of the variation in y. Get that word. That was the most missed question on the last test. It's usually the most missed word on this part of the thing. People don't say the variation in y. Well, what is y? It's nicotine is explained by tar. And it's milligrams of nicotine, milligrams of tar. Is a linear model a good model? We look up here. Now I think there's some ambiguity to this one. I could have students say that those are random residuals. I could also have students say it's patterned. I really don't even care. I can kind of see a little bit of both. It's just, if you say it's random, so on E, I'm going to do this one on another page here. If you think that's random, the residuals are random. So yes, a linear model is appropriate. But if you think there's a curve to it, you say no. The linear model isn't appropriate because the resids are curved or patterned. I can see both. And really, sometimes they kind of give you ambiguous ones in the idea, but what you can't say is you can't intermix those. You can't say they're random, so then it's not okay. Or you can't say it's curved, so it is okay. We just want to get the right thing with the right thought process. All right. Low predictions are likely to be accurate or inaccurate, and how would they be? Okay. So what are we talking about? Up here in the residual plot, if we were to predict something really low, down here it says these are the predicted residuals. So the low predictions, in terms of their accuracy, okay, this one too, I could kind of go either way. It's not going to be very far off because they're like within 0.15. It depends on what this thing is. I mean, 0.15 milligrams isn't necessarily that far off, but in terms of our slope, could be a little bit distance away. Like these are much closer in the middle. So I'm going to go with this one, that the low predictions are overall somewhat close. Somewhat close, that's supposed to be the word close. But overall, they're likely to be too high. And you might say, what do you mean too high? Well, the prediction is always the line, and this is what actually happened. What actually happened is lower than what was predicted. Okay, next one, is a linear model a good model? Well, not really, because the residual plot changes in variance, or it thickens. You can see it gets wider as we go. What ways would low predictions differ from high predictions? This is the reason it's not as good a model. Low predictions are going to be over here, and the way they would differ is a low prediction is going to be close to the red line, so the low predictions will be more accurate. But the high predictions will vary more. They're more likely to be much farther away from the line. Okay, so low predictions will be more accurate, but high predictions vary more. Tell me to back up if you need me to. I'm going to keep going ahead. All right, here we got a residual plot, and I think this residual plot, again, how do I know it's a residual plot? You look on the side, and it usually is going to say residual, but I think that's fairly patterned. So is a linear model an appropriate model? No, because the residuals are curved. But that doesn't mean you can't use it for something, and we're going to use it for something here. It says a car traveling 55 miles per hour actually got what gas. Now, a lot of times when I do these, I got to be careful because I mess up when I write the question. So I got to make sure I do this right. But they've got an equation here for fuel efficiency. It's up here. Equals 32 minus 0.1 times the speed. So I'm going to put 55 in for the speed. I'm doing part B. I'm just doing it down here. I've got a little more room to work. Okay? If I put in 55, what I get for the fuel efficiency is, that would be 5.5, take that away, 26.5, I think. Tell me if I do something wrong on that. Now 26.5, it says actually got what gas mileage. Over here, these are the predictions. So 26.5 is right here. So I want to figure out this dot. What's that dot? What's the actual residual? So the actual residual, this looks like 2, 2.5. I don't know. The residual might be like 2.7. Now, any estimate there, even if you said it's 2.5, that's fine. Let's remember E equals Y minus Y hat. So if that residual is a positive 2.7, we take Y minus Y hat. Here's our Y hat, 26.5. We add that on. And the actual mileage when we add that back on is 29.2 is my best guess. You might see, something different on my answer key. Maybe I have 29. Maybe I went with that being 3. Whatever. Okay. Everybody might estimate that a little bit different, that dot. But the idea is, what did you estimate the dot at? And then did you do the math from there correctly? Car traveling 65 miles per hour actually got what gas mileage. So now we have to do this one the same way for part C. So we're going to put that also into the equation. Fuel efficiency equals 32 minus 0.1 times 65. You get 25.5. We're again going to use this. We've just figured out the predicted. We got to figure out the residual, so you go back to here to 25.5, and that one I think is pretty clearly going to be 1. Okay, I mean, somebody says, oh, I want it to be 0.99. Fine. To me, you're wasting your own time. But the actual miles per gallon then for this one should be 26.5 miles per gallon. Because the residual is 1 above. So again, the residual plot's still useful, even though it's patterned. It's just not, the linear model wasn't appropriate, but it doesn't mean we can't use it to figure out stuff. Okay, so, I don't know. Do we need to do all of these? Maybe just a couple. I don't know that I want to do all of these. I'll do a couple for like A. It says ln. We didn't do one like this. ln of y equals 1.2 plus 0.8 times 2. So one of the things, in terms of doing these, I do have an answer key posted, so you can check all these. Hopefully I have all these correct on there. But if you put this in, you're going to get 2.8, and that equals the ln of y, which is the natural log of y. So you're going to need to undo that. And one of my pieces of advice on your calculator is you look for where the natural log is. The natural log is on this button, if you see me moving my mouse here, and the opposite of the natural log is the e raised to the power. So if you take e to the 2.8, you get 16.44, and that will be the answer. To undo the natural log, you simply take e to that power, you're going to get y, e to that power, and you get the 16.44, and that's going to be the answer. But you have to undo what is done in each of these problems. So part B is the square root of y equals, and once you've put this in, you get that's 2.8. Now I get a lot of students who do this. They take the square root of 2.8. If you do that, you've got a double square root on that side. That's not going to undo that, so that is an incorrect thing to do. You don't take the square root. You have to square 2.8 to solve this one. So the answer to B is going to be 2.8 squared. And that's going to be 7.84. C says 1 over y equals 2.8. And you say, why is it always 2.8? It's the same equation over there. So if I continue to put 2 in, I'm getting the same thing. D is going to be a little bit different, so be careful there. But how do I undo this? This is a reciprocal. So you can either do 1 over that, that's going to do the reciprocal, or you can raise it to the -1 power. That's the same thing. It ends up being 1 over 2.8. So again, however you want to look at it, it'll be the same thing, 1 over 2.8 or 2.8 raised to the -1 power. Same thing, 0.357. Okay, this next one. This next one doesn't have anything with y. It's 1.2 plus 0.8 natural log of x. So if you type it in, you get 1.75. That one is what it is. Okay? So that one's 1.75 for that one. D. Log y equals, this one would be back to 2.8. Look on your calculator, you take 10 to the power because the log is undone. That's the log base 10. It's undone by this. You get 630.95. We'll call it 631. Okay. So this is number 6. I'm gonna leave that one. I'm not gonna work through all those. Everybody, do we think we can handle those? There is an answer key on there. Okay, if you have questions. All right. So jumping up to number 7. 7, part A, describe the association. If you're asked to describe an association, we haven't done that back in since chapter 6. FUDs in context. We have weight, but be careful here. It says weight in thousands of pounds. Okay? The association between weight and fuel efficiency, which is miles per gallon, is, we got to look at it. I think it's pretty linear. So first I got the context by saying it's between weight and fuel efficiency. Then I got the form saying it's linear. We have an r squared. Now r squared looks like it's 65.9. Does that look like 65.9 to everybody? For r squared?
I think it's
85.9?
Yeah.
Well, then it's even stronger. So I'm going to take the square root of that. But you have to turn it to a decimal to find r. So when I take the square root, remember, right away you might say r is 0.926, which is definitely strong. But if we actually did find r, which I don't think we have to do in this problem, it's negative 0.926 because the association is negative. It's linear, negative is our direction. Strong, since it's above that 0.75 threshold, and I don't think there's any outliers. Okay? Here's the regression. What does the slope say about the relationship? So, what does the slope of the line say about this relationship? We predict now be careful, again, it's negative 7.65 miles per gallon over 1 more 1,000 pounds. So we predict 7.65 miles per gallon less, there's the negative, for 1 more 1,000 pounds of weight. You could just say for 1,000 more pounds of weight. The reason I do it as that 1 more 1,000 is just to stay consistent. You think a linear model is appropriate? Again, I think this one's ambiguous. I can see a curve, and these are all above, these are all above. So I'm going to say no, the residual plot is curved, but some students might think that's kind of random or random enough. By the standard I try to give you, on the left side they're all above, on the right side they're all above, in the middle they're all below, so I think it's curved. I think it's patterned. But if a student said, well, I think it's random, then as long as they fit that with one that's a little bit more confusing and said if it's random, then it's okay, I would be okay with that. Okay. Place a point on each graph that meet the following criteria. So here, we want one, we're looking for one that's 1 and 4. We want it to be an outlier, so we want it to be outside the pattern, and then we want it to have a small residual. Well, an outlier with a small residual, if I place it here, it's going to force the line to be like this, and it's going to have a small residual. Now, there are some other places I could put it, but it's going to have a small residual. Now, that one also happens to have high leverage. It doesn't mean it can't meet some of the other criteria, and that one would also be influential. Okay? But I did meet the 2 criteria. That's the important part. On B, it says we want it to be now have all 4 of these things. So actually, that one, again, could be all 4. I want to go back and rethink, okay, if there's a way I can get that one without the leverage and without the leverage. Okay, could be like here. Now that one won't have influence because it won't change the slope. So that one might be a little bit better. It's definitely going to have a small residual. It still has some leverage, though. It's hard to get that one without some leverage, you know. Now the next one, we want an outlier, has leverage, and a small residual. Well, I'll just put it in line, and it's got those things. But it's not going to be influential because it's not going to change the slope. But the next one, we want 1, 2, 3, and 5. The line would be like that if that point wasn't there, but with the point there, it's going to be like that, and it's going to have a fairly large residual. So this one, I don't test on anything like this, but it's just kind of an exercise to make sure you're getting those ideas of what large, small residual are, what happens if you put a point in line or not in line. And there were some like that on that last quiz that everybody hated, right? Because I put 2 of those problems on that were really long. Okay. Which one's the best regression? Well, this one I see a curve, this one I see a curve, this one I see a curve. That one at least seems the most random. So if I had to pick, it's the 4th one, which is the best regression 4. It has the most random residuals. And this is usually what I test on, is something like this. What's the equation? The equation is the square root of speed. And where am I getting that? I'm getting the dependent variable equals. Now we need B0. That's B0, that's B1. Don't get those mixed up. It's very easy. Is that a negative 10? I think it's a negative 10, isn't it? Yeah. Minus 10.37 times stopping distance. Okay? Then, could you use that? Could you put it in? It's the same as those problems where we undid the square root, so on and so forth. Which one's the best choice? Well, they all have their issues, but these three are clearly curved. Now this one, we can argue it's got thickening variance and should be ruled out as well, but at least it's got some ability to be random. So if I had to choose, I am going to choose the third one, which is the log, because it is more random. Make sure you always say residuals. Write the equation. So the equation here is going to be log of time equals 0.1327. Again, B0, then B1, plus 0.18498 times the amount. Predict the amount of time needed to get 8 bacteria. So we need to put that into the equation. Again,
You said there's an answer.
should be one on Classroom. Once you put that in, you get 1.61. Remember, the opposite of a log then is 10 to that power. So if you raise 10 to that power, we should get 40.98. Assuming these are something like seconds or something. Predict the amount of time for 12 bacteria. You got to do the same thing. Put that in. Go 10 to that power. We get 225.44. So time is 225.44 seconds.